All right, sorry about that, everyone. Apparently, my free trial for this recording software ran out, and I had a 15-minute time limit on my recordings, so I just had to subscribe for the year. So now I have unlimited time. So this is part 2 of chapter 8. Sorry about the break. We're going to pick it back up with open circuit spirometry. So before I was cut off, I think we were talking about the concentrations of gases, right? Now, all over the planet Earth, these are the rough percentages of the gases in the air around us, okay? 20.93% oxygen, 0.03% CO2, 79.04% nitrogen, okay? Now, there are things that make that vary, right? So the barometric pressure will change those percentages a little bit. So you probably have heard, like, if you're up on top of a mountain, if you're at altitude, there's not as much oxygen up there because there's less pressure pushing the oxygen down on top of us, right? So the percentage of oxygen at altitude might be a little bit less, okay? Other things that we deal with much more commonly can affect this somewhat as well. So air temperature, the humidity, and then in addition to barometric pressure, like I said earlier, those are 3 variables that we need to consider as we're measuring gas expiration. Okay, so as you'll see next week in our first lab, before we ever do a test with our metabolic cart, we have to calibrate the cart and put in barometric pressure, temperature, humidity, so the computer will know how those variables affect the concentration of gases coming in. So then as we expire, we're sort of comparing accurate information, right? So we do have to calibrate the cart based upon those factors, okay? But in general, this is the percentage of the gases in the air around us, okay? So again, this equation, you don't need to really worry too much about this. But what this shows you is VO2 stands for oxygen consumption. So how much oxygen are we consuming from the air around us and then using to produce ATP, right? Oxygen consumption is a function of the volume of inspired air at a known percentage of oxygen minus the volume of expired air times the known percentage of oxygen, right? So we're looking at, we know how much is coming in, we're measuring how much is coming out. So the difference between those two things is how much we're consuming, and oxygen consumption is then used to predict energy expenditure. So there are a few different techniques you can use for indirect calorimetry. The bag technique, this is obviously, if you can look at this picture, this is a very old picture. Prior to the advent of modern technology that we use now, so I'm talking about, like, this is like back in the 1970s, they would expire the air into a bag and then they would take that bag and analyze the contents. Again, not a very inefficient. To contrast that to now, we have portable open circuit spirometry devices, right? So this is a cyclist who has a gas analyzer here on her back. She's inspiring air from outside through the front, and then she expires through this tube into the gas analyzer, okay? So what we use in labs is kind of a hybrid of these two things, and it looks more like this. Okay, so up here on the top right corner, this is a metabolic cart. Okay, so this is specifically the Parvomedics. That's just the brand, the Parvo metabolic cart. So up on top of the cart, we have just a standard computer. Down here, this is the gas analyzer. So right, this is not a gigantic piece of equipment either. It is bigger than what we see here. But then what we have over here is the what we call the shoot, the name is escaping me right now. It's not super important, and we'll talk about it in our next lab, but we'll hook a hose, as you can kind of see it here. So this is an example in this picture of a resting metabolic rate test. So this is, we're just measuring resting energy expenditure. So the person is lying down. There is a gas collection bubble and a hood that we place over their head and chest. And there's a hose that is hooked up to the back of the bubble. Sorry, that keeps happening. This person, she is breathing in air from the room through this hole here, okay? And then she is expiring out through the hole in the back that it has the hose attached to. And as you can see, the hose runs around and is plugged into the gas analyzer. This is these are all very old pictures, but they kind of show you what it looks like pretty generally. The equipment that we have is updated above this, but the concept is very much the same, okay? Now below, again, this is a very old picture, but this shows you sort of what an exercise test looks like. So right now what they're doing is a treadmill-based, what we call a VO2 max test, and we're going to do this 2 labs from now. We have a very fine subject, and the subject is actually me running on the treadmill, and my expired gases are being collected, okay? But what you can't really see well is this guy, he's running on the treadmill, he has a face mask on, there is a breathing valve here with a hose that is attached to the metabolic cart. So again, he's breathing in air from the room, open circuit, right? And he's expiring his gases into the gas analyzer. And the hoses are hooked up to this piece on the metabolic cart, okay? So everything they're expiring, and I should tell you that in the case of exercise testing, we put a nose clip on the person because we want all the air to be coming out of their mouths so we can measure it. When they're doing a resting test, because we're using this bubble, they can breathe out through the mouth or the nose, and we'll still collect it. But during exercise testing, we have to use a nose clip. Now, if we jump back here, this person has a mask that covers the nose and the mouth. So in that case, you don't have to use the nose clip. In this picture, and this guy, this is not an accurate picture because he doesn't have a nose clip on. And this valve is much older than the ones that we use, but the concept is very similar, as you'll see next week, or actually that'll be in 2 weeks. But you clip off the nose, so all of his expiration comes out of his mouth, and then it is collected through the hose into the gas analyzer. Okay, so again, we use these carts, this metabolic cart, to measure oxygen consumption. We can do it both at rest and during exercise, okay? And by measuring oxygen consumption, that is a direct reflection of energy expenditure, right? So jumping way back to where we started, rather than putting somebody in a tank and measuring their heat production, which is not a great way to do it, we can measure their oxygen consumption and use that to then predict energy expenditure, okay? So just to summarize real quick, open circuit spirometry, because that is one of your lecture study questions. Or maybe it's the critical thinking, I can't remember which, but it's on one of those assignments. In both cases, rest and exercise, they're inspiring fresh air from the room. They are expiring into the gas analyzers, and we're measuring the difference between O2 and CO2 coming in versus coming out, and that tells us oxygen consumption, okay? Car calibration, as I mentioned, we do that prior to every test to account for the changes in barometric pressure, air temperature, and relative humidity. Where I live in the city of Louisville, Kentucky, the humidity and the barometric pressure change pretty frequently because we're in a valley. So as weather comes in and out, those variables change a lot. Where you all are up in Ohio, it's probably not quite as drastic, but still it's going to change, you know, minimally every single day. So you want to make sure you calibrate it before every use. So what information are we getting out of this? Now, again, in our labs, you'll see this sort of firsthand, and we'll talk about it more. But I wanted to give you a brief list now, just to introduce the concepts to you. So chiefly, the main thing is the oxygen consumption, right? VO2, that is a direct reflection of energy expenditure. And as we talked about in our last lecture, VO2 max is a measurement of somebody's aerobic capacity. So what is their maximal ability to produce energy aerobically, okay? So the most common test that you do with a metabolic cart is a VO2 max test. And we will do 2 of those in our labs, a treadmill one, and then we'll do one on the bike as well. So you'll get to see what those look like. During the VO2 max test, we'll collect data. And really all of the data that we have listed here are things that we're going to collect and write down on our lab assignments. A second thing that we can measure is what's known as a MET. So a MET is another real basic way to express energy expenditure. At rest, we all have a MET level of 1, okay? So 1 MET is equal to resting energy expenditure. 2 METs would be double your resting energy expenditure, okay? 10 METs would be 10 times your resting energy expenditure. So during a VO2 max test, when somebody is exercising at their maximal capacity, let's say their VO2 might be like 55 ml per kg per minute, their MET level is going to be probably somewhere around 12 to 15, okay? Again, don't worry too much about that now. I'm just introducing some of these terms to you all. The next one is a measurement of, again, the O2 to CO2 concentrations in the expired gases, okay? There are 2 terms that we'll use to reflect that. One we use at rest, and that's the respiratory quotient, the RQ. The other one we use during exercise, and that's the respiratory exchange ratio, the RER. We're going to talk about those 2 values to finish up the lecture. So I'm going to come back to those in a second, but let's carry on. Another thing that we measure during an exercise test is the volume of expired air. So not just the gas concentrations, but how much air are they blowing out per minute. Okay, obviously as exercise intensity increases, that's going to increase in a linear fashion. We'll measure respiratory rate, so how many breaths per minute. Obviously, that will increase with exercise intensity as well. And then lastly, this is more important for the resting metabolic rate test, which we'll do next week, is the amount of calories they're burning. How we measure it is based upon the current level of energy expenditure. What would their caloric expenditure be if it extrapolated for a 24-hour period, right? So if somebody wants to know, and a lot of people, if they want to lose weight, this is valuable information. How many calories do I burn per day, right? We can measure that using the metabolic cart and give them an accurate number of how many calories they burn per day. And they can use that to then set how many calories they are going to consume through eating to help with weight control, okay? So what I want to finish up with is to go into this respiratory quotient a little bit more, because this is valuable as well. So if we just kind of take a look at this first bullet point, the things that we eat, carbohydrate, fat, and protein, when they're broken down and converted into ultimately glucose, amino acids, fatty acids, and then ultimately into ATP, they require a different amount of CO2 and oxygen to be broken down, okay? So in the gases that were expiring, we can look at the ratio of CO2 to oxygen that's being expired and determine what the primary fuel source is, be it fat or carbohydrate or protein, at a given time, okay? Now at rest, we use the respiratory quotient. So during the resting metabolic rate test, we'll record the RQ, okay? Usually the RQ is going to be somewhere between 0.70 and 1.0. And we arrive at those numbers by using this equation here. So at a 1.0, CO2 produced and O2 consumed are going to be even, right? Say 6 produced, 6 consumed. That gives us a ratio of 1.0. Usually, we are consuming more, at rest, I should say, we're consuming more oxygen than we're producing CO2, okay? And when that's the case, the ratio is less than 1, okay? So, when we have a ratio of 1.0, again, we have an even number of 6 CO2 and 6 O2. That number is produced when we are primarily utilizing carbohydrate for fuel, okay? Because carbohydrate requires an even number of CO2 and oxygen to metabolize. Again, giving us the ratio of 1.0, okay? We'll come back to that in a second. Let's look at fat. Fat has an RQ of 0.70, 0.70. And we arrive at that number because it requires 16 CO2 and 23 O2. So more oxygen is consumed versus CO2 produced, giving us a number of 0.70. So what does all this mean? I'm not worried about you guys remembering these equations. What I want you to take out of this is the RQ for pure carbohydrate is 1.0. The RQ for pure fat is 0.70. Protein does not usually contribute much to the fuel supply, okay? It only does if we're like literally starving, would your body start metabolizing protein, or if you're doing very long duration exercise, like I'm talking multiple hours. Usually over 99% of the energy that your body is using to make ATP comes from carbohydrate and fat. Therefore, some people call the RQ the non-protein RQ, okay? So for the purposes of our discussion, we're not going to consider protein at all. We're just going to focus on fat and carbohydrate because during normal conditions, those are the two things where we get most of our energy from. So moving on. During exercise, again, we're still looking at those two numbers, CO2 production, O2 consumption. But we just changed the name of the ratio. I don't know why exactly they do this. It's just to make it confusing probably. But again, at rest, we look at the respiratory quotient. During exercise testing, we just call it the respiratory exchange ratio or the RER value, okay? And what we'll see during our exercise test is this number will change quite a bit. Now, during our resting metabolic rate lab next week, the RQ should stay pretty consistent, okay? And because the person who is our subject is resting, they're going to be using mostly aerobic metabolism, which means they're going to be using primarily fat as fuel. So their respiratory quotient during the resting metabolic rate test will be closer to 0.70, okay? Now, during our exercise test, what we will see is at the beginning of the test, the person is using mostly aerobic metabolism. So their RER is closer to 0.70. But as the exercise intensity increases every stage, the RER is going to creep up closer to 1.0, which means they are starting to use more carbohydrate for fuel, okay? And that's because they are beginning to rely more on glycolysis. Remember, aerobic metabolism can fuel light to moderate intensity exercise. But once we start doing high intensity exercise, we switch over to using anaerobic energy production, which is glycolysis, okay? Glycolysis can only use carbohydrate for fuel. It cannot use fat, okay? So that's one way we know that the subject is progressing to their max level of energy expenditure, because now we see that they're primarily using fat for fuel, okay? So what we'll do during our exercise test is we're going to monitor the RER. And as the RER gets to 1.0 and above, we know that the person is going to need to end the test pretty soon because they've got to their max exercise capacity. So again, 0.70 is pure fat. It's very rare that any human is ever relying only on fat for fuel. You know, we talked about this in class before, that usually you're getting a combination of energy production from all sources. There's always going to be a slight anaerobic energy contribution. So there's going to be some carbohydrate use. So usually people, when they're exercising at a low to moderate intensity, they're going to be at an RER more close to 0.85, which would indicate a 50-50 fuel split. Half their energy production is from fat, half is from carbohydrate. Okay. But then again, as they progress to max exercise intensity, the RER value gets to 1.0, meaning that they're using pure carbohydrate. Now, I know your head is probably spinning at this point. You're like, what are all these numbers? What is this guy talking about? When we do our labs, this will be much more clear to you because you'll see these numbers in action. They'll be recorded in real time. Today, I just wanted to sort of introduce the terms to you and get the numbers in your head somewhat, okay? So don't worry too much about not understanding this right now. We'll talk about it a little bit more in the labs for sure, okay? Now, this sort of summarizes a lot of what I've talked about. So I'm going to skip some of these bullet points, but make sure that you take the time to read through them again just to enhance your comprehension. What we'll see at the end of the VO2 max test is the RER is going to start going above 1.0. Now remember, 1.0 means CO2 and O2 are even. Higher than 1.0 means now CO2 is starting to get higher than O2, okay? And that again is a sign that the person is exercising at their max capacity, okay? So all of a sudden, as we are ending or getting to the end of a VO2 max test, all this extra CO2 starts being expired from the person's lungs, okay? So where is that coming from? Well, to give you the answer before we dig into exactly why, it's coming from lactic acid, right? So remember, when we're relying only on glycolysis for fuel production, we're doing that because oxygen is not available. Because oxygen is not available, we are producing lactic acid. Remember that, look down here at this equation. As a result of glycolysis finishing, we're left with these two products, pyruvic acid and hydrogen. When oxygen is available, these two things, Pa and H, can go to the Krebs cycle and the electron transport chain. But when oxygen is not available, those two things combine to form lactic acid, okay? Lactic acid accumulating, as we saw last week, is a problem, okay? So one way that our body tries to minimize the accumulation of lactic acid is by using what we call a buffering system, okay? So we have several buffer systems in our body. The most important one for exercise physiology is known as the bicarbonate buffer system, okay? Bicarbonate is a molecule that is very similar to baking soda. And the formula for bicarbonate is here, HCO3. Okay, so all of us have this in our body, in our cells, and it helps us minimize lactic acid and helps us maintain proper pH balance. So the hydrogen that is partially composes lactic acid can be broken down and combined with bicarbonate. So we would strip the hydrogen off the lactic acid. The hydrogen would combine with bicarbonate to form another acid, which is carbonic acid, H2CO3, that's carbonic acid. Carbonic acid is known as a weak acid, and it's weak because it falls apart very easily, okay? Now, even though it's formed from H plus HCO3, when it falls apart into two different molecules, which we see here, H2O and CO2, right? So the water is good for us. We can use that for many things. The CO2 is now something that we can easily get rid of by expiring air, okay? So what the bicarbonate buffer system does is it takes the harmful hydrogen molecule and ultimately converts it into two things that our body is more easily able to handle and deal with in the form of H2O and CO2, okay? So to summarize, this excess CO2 that we start blowing out at the end of a VO2 max test and that causes the RER to get driven up above 1.0, most of it comes from the bicarbonate buffer system and specifically the buffering of lactic acid, right? So again, at max exercise, we're relying almost 100% on glycolysis. Whenever we do that, a lot of lactic acid is being produced. If it accumulates too high, we have to stop exercising. So one of our body's lines of defense is this bicarbonate buffer system, where the harmful component of lactic acid, which is the hydrogen, can be bound to bicarbonate, which then forms carbonic acid. Then carbonic acid falls apart into water and CO2, okay? And that CO2 we expire through our lungs, okay? And really that's what hyperventilation symbolizes. Hyperventilation is basically just an accelerated rate of breathing, okay? When we're hyperventilating, we cannot carry on a conversation, okay? So if let's say you're running up a hill, let's say you're out running on a flat, you're with somebody, you can talk to them because you're not hyperventilating. But then you reach a hill, you have to climb a steep hill. Now all of a sudden, you two go quiet. You're not talking because you're hyperventilating, okay? And the reason why you're doing that is because your body suddenly has all this extra CO2 to get rid of. And that comes from the lactic acid that your muscles are producing while you're climbing up that hill, okay? So again, we'll see all of this stuff in action in our labs that are upcoming. Don't panic too much about this material, all these numbers. We're going to see these again. I just wanted to introduce these concepts to you today. So your tasks for the week are the typical ones: complete the lecture study questions, complete the critical thinking assignment, and then next week we will have a lab in place of the critical thinking assignment. So you'll have an additional video to watch of the lab test, and then I'll have a lab assignment that'll correlate to the lab that you'll have to fill out and complete, okay? So there is going to be some additional work when we have labs, but I hope you enjoy those because you're going to get to actually see some of this stuff in action versus just listening to me talk about it, and that's much more interesting. So hope you all have a great week, and I will come back and see you soon.